actually saying that a very small halo mass is related to the galaxy mass that is there of that galaxy inside the object currently. And this idea, this is clearly inconsistent with what I just said, where we expect that the galaxy being very compact should be relatively protected against the influences of of these tidal effects. So that's what led to this initial thought that in around 2004 and so on, where people said that, okay, slightly later actually, where people said that, okay, we should not do abundance matching between the galaxy properties and the current mass of the object. We should do a matching between galaxy properties and the mass which that object would have had if it had not gone through these dramatic effects. Okay, and that is not, then you can't really extrapolate. You would not know exactly what would happen. So a reasonable proxy for such a mass would be the peak mass. Okay, so that is where this idea comes from, because the galaxy and the halo have been kind of co-evolving all of this time. And then suddenly here, the halo started doing something completely different because of what was happening at its edges. So then the peak mass is a reasonable proxy of what the galaxy should have been doing. Okay, so this is roughly the idea behind abundance matching of, let's say, stellar mass or luminosity with something like M peak. So then which variable specifically you use, M peak or V peak or something else, this is a matter of detail. The physics is what I just described. So it's then worth looking at the differences in the mass functions of M peak and MVir, which is what I've done here. This is using a very similar code to what I showed you. It's just that instead of binning log MVir, I will just replace that with log M peak. Okay, so it literally, if I just go back into this will come to. So here it's still the same notebook. Okay, so here, for example, I can just replace all the occurrences of vir. There's these guys, and then these guys with peak. Okay, and this should work. And then let me also plot these two. And here also I will do peak. And in this case, I will also do a slightly different line style. So let's give them different line styles. And while we're at it, okay, so let's make these solid lines and let's make these dashed lines. And let's say the halos, we will give black color, and the subhalos we will give red color. So let's see what happens. Okay, there we go. So what you see is that the all halo mass function doesn't really change, but the satellite mass functions change when you go from vir to peak. So remember, solid line is mvir and dashed lines are m peak. And what you see is that the subhalos, when you count them using m peak, they have substantially larger masses. Okay, so that is also what I am trying to show here. Let me go back so it's clearer. So this is the same thing. On the left-hand side, I've used MVir. On the right-hand side, I've used MPeak. Okay, and you can see that the subhalo mass function has shifted to higher masses. Or another way of saying it is that if I look at the same halo mass, whether I'm counting MVir or MPeak, the number of objects that I count as subhalos with MPeak is higher. You see this horizontal line at the same 10 to the 12. This horizontal line is intersecting at a higher value than this horizontal line, which is at the same 10 to the 12. Okay, so when you count MPeak, your objects, for the same reason that we saw here, there can be a large difference in halo masses. Okay, so let's see. So this is what I wanted to say about MVir versus MPeak and the reason for MPeak being interesting from the point of view of abundance matching. Okay, so before we move on, so now I want to argue that abundance matching is a good thing to do, not only for the mass functions. So the mass functions and the luminosity functions will be matched by construction. But once you have matched the luminosity mass function to the mass function, something else should also come out right, no? Because this is just by hand you have done something. So the thing that you will look for is clustering. So we will come to this. This is the purpose of this session. So it will be kind of a mixture between talk and hands-on. So let me first maybe talk about this visualization. So we will come to clustering in a bit. So visualization is like a simple way of looking at clustering. Okay, so what I have done here is to show a slice of the simulation box. Okay, and the slice is something like 60 megaparsec on every side. And I have centered the slice at a particular place. And there is a thickness to the slice. I think I have used a 10 megaparsec thickness along the third direction. So I've plotted all the objects which lie in a 10 megaparsec region in this 30 by 30 megaparsec area. Okay. And the way I have plotted them is the centers, XYZ locations are the centers of my markers. The size of my markers is proportional to the virial radius of the halo that is sitting there. And I will quickly show you how this can be done in Matplotlib. And I think I have chosen a scaling just to make them visible. I have chosen a scaling so that the radius of every marker is 2 times the virial radius. Okay, if I had shown virial radius itself, the markers would have been much smaller. So I showed 2 times the virial radius, but this is 2 times the virial radius in proper MPC over H units. Okay, so from this end to this end, this is to scale. I have not touched that part to make it artificial. It is actually 2 times the virial radius. So now, okay, so that is one thing. And then Nishi has already done abundance matching for you. So now for every object, I know not only its virial mass and therefore its virial radius, but through spherical collapse, but I also know, its luminosity, its R band magnitude. So I have given colors to these markers where the color bar shows you the R band absolute magnitude. So I don't know if you can make out, but basically all the points that you can see very clearly, the big ones, they are very bright. Okay, they lie between -20 to -22. So these are bright, big objects. And what may not be perfectly visible is that there are tiny, tiny markers everywhere. And those tiny markers happen to also be bluish. So it's the faint objects which are smaller. And this is obvious from the fact that we did abundance matching to MVir or MPeak, right? So we did abundance matching to a mass variable, luminosity to mass. And spherical collapse says that mass and size are perfectly correlated. So if you give me the mass, 1/3 power of the mass is like the radius. So it is not at all surprising that there is a strong correlation between the sizes of these markers and their luminosities in such a plot. Okay. So this is one visualization. And here what I did is to simply show you separately the objects which are classified as centrals, that is living in parent halos, versus objects that live in subhalos. These are satellites. Okay, so the slice is the same. It's just that I'm showing centrals and satellites separately. So you can see, for example, there is this big object here. It has a lot of satellites. Okay, and all the satellites are very tiny. Their virial radii are extremely small, actually. Okay, because of this tidal stripping kind of effect. And there are a lot of them in this particular region, and many of them will be associated with this largest object, and there'll be some associated with this one, some associated with this one. So this is like a it is like a supercluster, if you like. So this is a cluster. This object itself is probably the host of a large cluster of galaxies, and then this collection of objects together form something like a very massive supercluster. Okay, so this kind of visualization you can do. So before moving on to more statistical measures of clustering, I'll just show you how this visualization is done. But obviously you can see from here that these tiny, tiny objects are pretty diffuse. The tiny objects which are centrals, okay, in the left panel, they are pretty diffuse compared to tiny objects which are satellites. They are all very strongly clustered. They only come in clumps like this, which is obvious. They are satellites of big objects. And the big objects also are visually kind of organized into these filamentary patterns, right, which you can sort of make out. Okay, so let's do a quick look at the code which produced this. So this is not part of the notebook I gave you. It's I can put it there also. It's not very difficult. I can just run you through what I'm doing here. Okay, so ignore this. Where is my visualization? Here it is. Okay, so I have to just set a few things. So just some variables for technical stuff. This Vmax Vmin is related to the color bar that I want to show. So I want to make the color range from a value of MR going from something to something. So that something to something is set here, minus 14.5 to minus 23.5. I have to choose a particular color map. There is a range of color maps that you can use. There is a web page. Let me see if I can quickly get it. Here. Okay, so if you look at, how do I, the zoom window is, okay. Okay, so this web page, I can put it into the Zoom chat. This is very useful. There is my chat. There we go. So this allows you to play with color maps. And okay, then I want to set a transparency for my markers so that they're not opaque. This is used later. Then this part is the thing which allows you to scale your markers to whatever size you want. Basically, you have to realize that you're plotting and the plot has some units, some pixel units. You want to convert them to MPC over H units. So you want to say that RVIR equal to, let's say, 500 kpc over H corresponds to so many pixels, right? So you need a scaling factor which does this conversion for you. And unfortunately, there is no good way of figuring out the scaling. So it's basically trial and error. So I have done that here. And if I had switched this on to true, then it would have shown me a circle with a radius of half the box size. And I just make that circle fit inside a square which has a size of box size. Okay, so that's how I did the trial and error. So I'll not go into those details. Then you may choose or not to choose to zoom into a particular region. I have chosen to zoom. That's why I showed you that. So let me just say zoom false so that it shows you the full box. And then I have to pick how much I want to scale up my virial radius by. So I told you that the radius of my objects is twice the virial radius. So that is this thing here. Okay, then I have to pick a thickness for the slice. So I had shown you the zoomed version where the slice thickness was 10 MPC. And when I'm not zooming, I have chosen a slice thickness of 4 MPC. Otherwise, it makes the field very crowded. Okay, these are just aesthetic choices. You can play with them on your own. Then I have to then I have to say how wide is my square. So when I zoom in, I was showing you a square which was 60 by 60 MPC. And if I'm not zooming, I'm showing you the full L box. Okay, you don't worry about this var dot. This is for some reason. I have initialized a class which has an attribute which has my box size, and I'm using that. And then where do I want to center my slice? So after looking at the unzoomed version centers the slice at half of the box size. After looking at that, I chose a particular point where I wanted to center, which was 60,150. Okay, so this is just technical choices. I then define some Zmin, Zmax, Xmin, Xmax, Ymin, Ymax based on these choices. And then I do my visualization. So here I am selecting the objects according to what I want. So I will choose objects whose z-axis is in the minimum and maximum of z. Similarly, y-axis and x-axis. And I just keep defining what is called a Boolean array, and I keep updating it. So this con select keeps getting ANDed with more and more conditions. So after these three basic conditions, on on the positions of my objects, then I'm also doing this kind of thing where the select vals is just this array of strings, all galaxies, centrals, and satellites. So if when so I'm looping over them, okay, for select and select vals. So the first one will be all galaxies, which means this if condition will be bypassed. Second one will be central galaxies, in which case I will update my selection to say only PID -1 objects. And in the last case, I will have satellite galaxies where PID not -1. All right. Then here are my virial radii that I need. So this is the virial radius calculation. Someone was asking me about this before. So this delta vir is the overdensity that Nishi was mentioning. It is approximately 200, depending on which definition you use. For virial density, it is this Brian and Norman thing that was being mentioned. And basically, I'm saying that I convert my masses into radii by taking mass divided by 4/3 pi times density to the power 1/3. Okay, so this thing rho c times E Hubble to squared is just critical density of the universe. Then using these virial radii, I set the sizes of my markers. And in Matplotlib, the convention is to give the area of the sizes as the marker size. So I'm doing pi r squared. And I am scaling up my virial radii by that factor 2. And I am converting from MPCH units or KPCH units into a scaling factor for pixel units. All right. And that's it. Now I just have, now the rest of the thing is just plotting. Okay, so I create a plot. I say make a scatter plot here and sorry, here. Okay, so I plot my X and Y locations with sizes set to the values that are there in this array and colors set to the luminosity for the appropriate sham variable. Sham variable in this case I've chosen to be MP. Okay, and then I define a color map, normalization, and I set some labels and I save the file. So let's do this. Here we go. So this is the full box, 0 to 200 MPC over H. Okay, and in a 4 MPC slice, you can see this is what the pattern emerges to be. And you can see the clustering automatically there. Large objects live in big clusters. Small objects are everywhere. And if I split the objects by centrals and satellites, this is what I get. So with centrals, it doesn't look very different because there are not so many satellites. So most of the objects you see here are in fact centrals. Only roughly 1/10 of them are satellites because of this mass range. And those satellites are here. They're not very clear, but you can see that wherever they are, they live in bunches. Satellites are very clustered compared to centrals. Okay, and basically this is what I was showing you in the slides. Okay. Good. So this is a very, very basic introduction to clustering. So now let's do something a little more statistically interesting. So let's talk about a statistical measure of clustering. So the simplest measure of clustering is the 2-point correlation function, which let me see if I can get rid of this. Yes. So the 2-point correlation function is a simple way of asking how non-random is your data set. So in conceptual terms, this is the kind of data set that we are talking about. It's a clustered set of galaxies. This is actually a mock catalog of galaxies. And we want to ask how non-random this is. So if I took the same objects here and I just redistributed them randomly. So this is like a 2x2D image. So if I just take all of these 2D points and I just draw 2 uniform random numbers, one for X and one for Y. And I just assign this as the XY coordinate. And I draw these uniform random numbers the way Jasjeet was telling you about in the first session. And I just scale them up. Instead of 0 to 1, I draw them between 0 to L box. Okay, so then the resulting distribution will look like this. It has the same number. In fact, it has the same objects. I've just redistributed them by drawing uniform random numbers. So visually, it is obvious that this is a clustered set and this is an unclustered set. Now I want to know how clustered is this clustered set? And the conceptual way of doing this is to take some kind of ratio. Okay, so here is the statistical way of defining clustering at the 2-point level. You ask, what is the joint probability of finding a galaxy at location x1 in a tiny volume delta V1 around x1? And at the same time, finding a second galaxy at the location x2 sent in a small delta V2 volume centered around x2. Okay, so this joint probability, suppose you were able to calculate, what you then say is that let us parameterize this joint probability in the following way. you ask, if I had an unclustered set of points, what would the joint probability be? So for that, you ask, how do you generate the set of unclustered points? Here it is. You drew a uniform random number between 0 to L box, another uniform random number between 0 to L box, and a third one for the third dimension. And then you just distributed these points. Now, if you follow the theory of stochastic processes, you will realize that doing a uniform sampling like this is basically creating and doing this independently. Okay, so when I draw a uniform random number, a set of 3 uniform random numbers for the first point, and then another set of 3 uniform random numbers for the second point, and so on and so forth for all the n points in my catalog independently, what I have done is to produce a realization of a Poisson process. And the probability distribution of the number counts in any given delta V volume for these Poisson distributed tracers is given by the Poisson distribution. Okay, and if I take a very small delta V, then the probability of finding one object in, okay, so first of all, probability of finding one object in one delta V and a second object in a second disjoint delta V for a Poisson process, these two probabilities are independent of each other. So the joint probability is just the product of these probabilities. And in the limit that this delta V is very small, the probability of finding one object in this delta V is simply equal to the number density, the expected number of points in this delta V, which is number density times delta V. Okay, so this is the infinitesimal limit of this Poisson probability. And these two are independent of each other. So I take one average n times delta V1 and I multiply it with average n times delta V2. That gives me the probability, this joint probability, which would have been there for an unclustered distribution of points. So I write the actual joint probability in the clustered distribution as this expected probability from the unclustered distribution into 1 plus some quantity xi. This xi, therefore, completely characterizes the non-randomness of this joint probability. Okay, so this xi is called the 2-point correlation function, and it captures how non-random is the spatial distribution of pairs of points. And now, depending on your underlying process which created this clustering, this xi can have different forms. So for example, in cosmology, we are generally interested in processes which are statistically homogeneous and isotropic. This was mentioned in the previous sessions also. And statistical homogeneity means that this xi will only depend on the difference between the locations of these two objects, the vector difference between x1 and x2. That is statistical homogeneity. And statistical isotropy will further tell you that only the magnitude of this distance, of this separation, will affect xi. So xi is just a function of mod of x1 minus x2 for statistically homogeneous and isotropic samples. So now the only question is, okay, if I want to measure this xi, what is a good estimator of xi? All right. So the first such estimator was put forth by, as you expect, by Jim Peebles in a paper by Peebles and Hauser. And it's given here. This is the Peebles-Hauser estimator. And it is basically a numerical way of thinking of this equation. So if I think of this equation in terms of probability, so if I convert these probabilities into numbers, right? Probabilities as fractions and therefore numbers. So what is this? This is just counting how many pairs of objects there are which are separated by some separation. And this part is counting how many pairs would have been there if the distribution were random. So that's exactly what is being done here. This 1 plus xi estimate is just the number of pairs that you expect to be separated by R, that you measure to be separated by R in your clustered sample, divided by the number of pairs that you expect to exist with separation R in a uniformly distributed sample. Okay, so this DD is this clustered set of pairs and RR is the unclustered set of pairs. So DD by RR minus 1 is the simplest estimator of the 2-point correlation function. And then when you go to observation, so this plot is from Zehavi et al. 2011, clustering in SDSS DR4, sorry, in DR7. When you go to observations, there are further complications due to, as Nishi mentioned, redshift space effects. So there are different ways of accounting for redshift space effects. One way is to basically try to integrate over them. So you know that they affect only the line of sight. So if you call the line of sight direction as pi, then you can define a new clustering measure where you do a two-dimensional clustering where you keep the line of sight direction separate and then you integrate over it. Okay, and you define a clustering measure which is called the projected clustering function, 2-point clustering, WP of RP. RP is the perpendicular separation, and this is what is the observable then. Okay, and what you see in observations, but for for conceptual purposes, just think of this WP-RP as just this 2-point correlation function, and this RP is just conceptually similar to the 3-dimensional separation R. So what you see in observations is that as a function of separation, first of all, the 2-point correlation function decreases by several orders of couple of orders of magnitude as you go by couple of orders of magnitude in separation. That is the first effect. Secondly, if you split your samples of galaxies by luminosity, then the fainter samples have a lower clustering strength on average compared to the brighter samples. Okay, so minus 22 and above is a very bright sample. Minus 19.5 and above is a faint sample. You see there's a clear separation between the clustering amplitudes for all separations, right? Across all separations, bright galaxies cluster more strongly than faint galaxies. So if abundance matching is a good description of the data, it should not only produce the luminosity function, it has to produce a luminosity function because you built it in. You made it produce the luminosity function. But if it is a good description of data, it should at least produce the 2-point correlation function also correctly. So we are going to look for two things now. One is that you give me any sample of galaxies, more or less its clustering amplitude should fall as a function of scale. So that is one effect that you should see. Second is if you split your samples by luminosity, then the fainter samples should have lower clustering than the brighter samples. Okay, so let's first see that this happens, and then we can, if we have time, we can discuss why it happens, why one expects on physical grounds this thing to be the case. So let me go to the hands-on part now. Now you can actually, I hope I am still with everybody. You can go back to your notebook that you got in the Google folder, in the Drive folder. And just below the mass function part, there is this thing called 2-point correlation functions. So using the same catalog, by the way, I should have mentioned, if I didn't mention, this is one of the catalogs that Nishi produced. Okay, it was not exactly the catalog that I gave him. I directly used the abundance match catalog. That's why I had to give these column names, which also have MR of MWIR and MR of MPeak. But if you use my catalog, which only has halo properties, then you'll have other halo properties, but not these luminosities. So this catalog is useful for us because I can now do abundance. I can do clustering split by different properties. Okay, so in this example, I have just shown you clustering using split, I think, by nothing to begin with, and then we'll do some splits. Okay, so what do we want to do? So first of all, we want to be able to measure this DD by RR business. Okay, so let's think about what this DD means. DD is just a pair count. So what I need to say is give me a separation R and a small range maybe around the separation, R to R plus DR. Okay, little r to little r plus. So let's say 10 MPC to 12 MPC separations. Now I go to my catalog and I ask, how many pairs of galaxies will I find whose separation is between 10 to 12 MPC over H? I need to do this counting. So now it becomes a question of how to do this counting efficiently. So to begin with, let's forget about efficiency and just do a boneheaded brute force technique. Okay, so that is what is displayed here. So let's, and just to make sure that code runs on time, I will first restrict the catalog to only a small subsample containing roughly 10,000 points. Okay, and 10,000, as you will see, is a reasonable thing to do in a short time. In fact, we can even make it smaller. Let's make it 1,000 points here. And the way I'm going to select this catalog is by saying, give me the upper, so 1,000 is some fraction of the total size. Okay, so the total size is this mocks.size, which if you remember from here, I hope my screen is readable. It's something like 780,000 objects. So 1000 is a very small fraction of it. So I basically say, give me that particular fraction of objects from the upper part of the masses. Okay, so I define a percentile of mass in terms of actual percentage. Is 100 times 1 minus this fraction, and I ask NumPy to give me the percentile of log mvir corresponding to this value. Okay, so it will tell, so it will print out something, it will tell you what it's doing. So in fact, why don't we just do that quickly? So I'll just comment out everything except just this guy. And let me just print out mvir PC, this percentile number, and the corresponding log mvir value that it has produced. Okay, so you can see that 1000 objects is less than 0.2%. It's almost like 0.1% of the sample. And it corresponds to a very high cut in log mvir. It's like 10 to the 13 point, like 3 times 10 to the 13 or so. Okay. So I'm only going to select objects whose virial mass is bigger than 3 times 10 to the 13, just to truncate the numbers. All right, so then let me just quickly walk you through the rest of the code, and we'll run it. Running will not take a lot of time. So here I am first selecting my objects. So I'm only taking objects whose log mvir is bigger than log mvir min. We will come back here and add a few more conditions. And I'm just, for convenience, I'm defining a new catalog called mocks downsampled. It's not really downsampled, it is just whatever, truncated, I should have called it truncated, where I take my original mocks and I just select those objects which satisfy the condition that log mvir is bigger than log mvir min. So if you're not familiar with this way of indexing, etc., you should read up on Boolean indexing. Okay, Boolean indexing in Python and NumPy. This is a very, very powerful technique to manipulate arrays in Python, in NumPy especially. Okay, so now I have my truncated catalog, and I just redefine my this end down variable to make sure that I'm actually talking about the catalog here. So let me just do this also. I will just stop the thing here. So I have restricted my mock to, in fact, exactly 1000 objects having log mvir bigger than this. Okay, good. So now I want to do clustering. So let me open this up. So I'm defining now a set of separation values, R bin. So in this case, for example, it would correspond to these particular bin centers, okay, roughly. So this is from Zehavi. I'm not following what she was doing. I'm doing my own binning, but conceptually, this is what she also did. She just defined a bunch of bins, and the bin edges will be somewhere in between, okay? So this R bin is the set of bin edges. And I was doing the same thing, if you remember, with the mass function also, right? Log m bin was the bin edges. Here R bin is the bin edges. And here I'm just using another NumPy functionality called log space. So I'm going from 10 to the minus 1.5 to 10 to the plus 1.5 MPC over H. And I'm defining 20 such bins. And then similarly to the log m center, I'm defining R center, R mid, by taking the geometric mean of these, because I'm getting log spaced values. So the bin centers, when I have log spaced values, are more reasonably approximated as the geometric mean rather than arithmetic mean. Okay. And then this dist2 bins is distance squared bins. This is just a convenient array because I don't want to take square roots inside my DD calculator. So here is my DD calculator. Okay, so what am I doing? So for the time being, forget about this and just think about this part. So I am calculating, forget also about this absolute value. FABS is just absolute value. Okay, so just think about this. DX is the difference. So this is going to go into a loop. Okay, and for the ith galaxy, this I calculate first dx, which is the difference between the x coordinate of the ith galaxy and x coordinate of all the galaxies starting from I plus 1 all the way up to the end. So this dx is not a number, it is an array. It has a length which is basically number n minus I. Okay, because it is going from I plus 1 all the way up to the end. So this is the difference in x value between the x coordinate of this galaxy and all the subsequent galaxies using some ordering. Doesn't matter what the ordering is. Similarly, dy is the difference between y of this galaxy and y of all the galaxies after it. And similarly, dz. Then I just calculate dx squared plus dy squared plus dz squared. These are the squared separations between this galaxy and all the galaxies after it. And I histogram these separations. So these are my separations, dis2. I put it into histogram with what bins? These bins that are defined here. Okay, that's it. So for this particular galaxy now, I have a histogram of the pair counts with all the galaxies that are ahead of it in the ordering that was chosen by the catalog. And once I have this, all I have to do is loop over them, loop over all the galaxies. Okay, so n minus 1 galaxies, because the last galaxy will not have any pair in this way of doing it. So I define an array which will have enough space to hold all these paired separations. So the separations array has a length of 20. Okay, so and this R bin and this dis2 bins have the same size. So that 20 is going to come here. All right. Sorry, R bin has a size 20. I have made a mistake here. No, this is fine. Okay, so this R bin has the bin edges. Dis2 bin also has bin edges. So the number of bins is the number of bin edges minus 1. So I need to be able to store that many values because the size of this frequency array will be equal to number of bins minus 1. Okay, so that is this part. And I am doing this for n minus 1 galaxies. So I am defining temporary storage. This frequency temp, it has temporary storage for n minus 1 galaxies. So now I go into a loop over n minus 1 galaxies. For the ith galaxy, I run this, I invoke this function, brute force, for the ith galaxy. It will calculate dx, dy, dz. It will calculate the squared separations. These are arrays. It will bin these squared separations into my dis2 bins, and it will spit out this particular dis2, this frequency. Okay, this frequency array. And the result of that will be stored in frequency temp for the ith object. So I'm doing this for all n minus 1 objects. And my final brute force DD calculator is just a sum over these temporary frequencies over all the galaxies that are there. Okay, all these n minus 1 galaxies. So this sum over axis 0 means it will sum over all of these galaxies. Okay, that will finally collect together all of the DDs. So, okay, so that is this sum. And then finally, I have to normalize in order to be not sensitive to how many galaxies I'm talking about. Okay, because that is part of the definition of DD. It does not depend on the numbers. It is a relative definition. It is a relative probability. So I have to remove the total number of pairs that I could have counted. And because of the way I'm counting these pairs, I'm only counting distinct pairs. You see, for the ith galaxy, I only count pairs with I plus 1 and following. So the number of distinct pairs in a set of n down galaxies is 1/2 nn minus 1. So I divide by that number of distinct pairs. So I hope this is clear. If there is something unclear about what I just said, you please ask me just now itself. So I'm assuming, okay.
When you have defined the frequency temp, then you have taken it as a two-dimensional, not two-dimensional array. Two-dimensional array.
Yes, it is two-dimensional. Yes.
Yeah, but when you are using it for DD brute force,
yes,
it's only giving the only frequency.
Correct. So this is okay. So do you agree that this freak here is a one-dimensional array of size 20 minus 1?
Yeah.
Yeah, that part is clear. So this output here is a size 20 minus 1, 19 size array. and I am assigning it to freak temp I.
Okay. Okay.
So freak temp I is also a 19 size array.
Okay. Okay.
Okay, and
Okay.
I is running from 0 to n down minus 2.
Okay. Okay. Yeah.
Okay, so one by one, I am assigning freak temp I as 19 size arrays.
Okay. Okay.
And then in this step, I am again converting this. So now I'm converting n down minus 1 comma 19 size array into a 19 size array by summing over the zeroth axis.
Okay.
Okay, so I'm summing over all the galaxies that I counted and I am normalizing.
Okay.
Is that okay?
Yeah. Yeah.
All right. Is there another question? Okay. So if that is fine, then let's move on to the next part. So this is the numerator of that Peebles-Hauser estimator. For the denominator, we need RR. Now, in a generic setup, what you should actually be doing is to actually take a sample of random points here and repeat the exercise, right? This DD brute force calculator, you could also feed it into, I mean, the set of objects that it works on could also be a randomly distributed set. So you could do the same thing there, and it would give you a perfectly okay estimator of RR, all right? But the issue is that if now the question comes, how accurate is the estimator, right? What are the errors on the estimate? So now here you should realize that in DD and RR, if both of them are going to come from numerical samples, then both will come with an error associated with the fact that the numerical sample has a finite size. So in this case, I only have 1,000 objects for my clustered set. So that will define some error on DD. And that is not in my control, because if I observed a galaxy sample from SDSS and SDSS told me that in a certain RA, deck and Z range, there are only 50,000 objects, then I cannot do anything about it. Okay, so DD has to be calculated with whatever you get. But for RR, it is completely in my control. Okay, so for RR, in principle, if I can beat down the errors to as low a level as I like by simply taking a very, very large number of random objects, if I want to do it numerically. Okay, and in a realistic setting where I want to do the measurement of two-point correlation function in SDSS, for example, this is what people exactly will do. They will sample the SDSS sky and the SDSS selection function uniformly with a huge number of random points. And then they will apply this kind of DD estimator. Not, of course, not exactly this. This is a very inefficient estimator. We'll discuss efficient estimators in a bit. But conceptually, they will do the same thing for RR as well. Okay, so this is what one should do in a generic setting. But we are actually talking about periodic simulation boxes. And in a periodic simulation box, there is an even nicer way, even more accurate way of calculating RR, because for such a box, you can actually calculate RR analytically. Okay, so you can just analyze the statistics of Poisson processes and calculate pair counts and impose the condition of periodicity. And it turns out that there is an analytical function that you can write down for the form of capital RR as a function of little r. And right now I will not go into details, but all I will say is that if the separations that you're talking about are less than 1/2 of the box size, then this analytical function is simply this thing here. Okay, it is 4 pi r squared dr. That's it. So in the range little r to little r plus dr, the analytical function is 4 pi r squared dr. And if I want to do it on finite separation delta r, then I'm doing 4/3 pi times r1 cubed minus r whatever, r next cube minus r previous cubed. Okay, so that is what is done here. And I have to normalize by the box size cube, by the box volume. So this is coming from analytical calculations. So it makes life very simple. I don't have to spend any time calculating RR for a periodic box. Okay, so that's it. And this is just some memory cleaning. I have created a large array here, so I'm not going to use it. So I just delete it and give back memory to the system. Python 2 is not very good with memory usage. So that's why one has to do such things. So now let's just run this. And it's done already. Okay, for 1000 objects, it takes no time. So let's just plot this. So plot, I want to produce a plot similar to this. So log scale on y-axis, log scale on x-axis. Okay, and I'm just plotting the midpoints of my bins and dd by rr minus 1, just this much. Here we go. It looks reasonable. Okay, it's very noisy here because we have only 1000 objects. I will now quickly change to 10,000 objects also. But already you can see that it is falling by roughly the correct order of magnitude also. Okay, within 2 orders of magnitude, within 1.5 orders of magnitude here, it has fallen by roughly 2 orders of magnitude here. Okay, so that's not too bad. Let's increase this by factor 10, taking slightly more time. And it's done. And here we go. Okay, so you get now, this time notice that it has gone, because it has chosen more objects, it has gone down lower in mass, right? Earlier it was 13 point something, now it's 12 point something, and the clustering has changed. Okay, so now let me quickly go back to the slides where, okay, so let me show you this slightly more complex version of this code. Okay, maybe it's worth doing this. Okay, so this is a slightly different notebook where I have a little more sophisticated set of routines which I have libraries for. I have written some libraries of my own which I have called here. So they will just produce output in some fancy way. Okay, so they will give you some nice looking output. So I wanted to do a timing test for a different set of, well, let's see how I want to do it. So, okay, maybe I will do this a bit later because this is just a way of comparing different algorithms and doing a timing analysis for checking efficiency, etc. Okay, so we'll do that later. For now, let's just focus on the results. So let me go back here and I'll show you the results of our sham. Okay, so this now you can also start doing. We'll just do this quickly with the results that with the notebook that I was showing you using selections on objects by different properties. So let me just show you the results and then we can go back to the notebook. So what I did was I ran a notebook very similar to the one I showed you. Okay, and just that when I did my conditioning on selecting the galaxies, instead of selecting by halo mass, I have selected by luminosity. All right. And in the left panel, I selected by luminosity with the M-peak sham. And in the right panel, I selected by luminosity with the M-vir sham. That's the only difference between the two. Otherwise, the luminosity ranges are identical. Okay. So the solid lines show you three different luminosity ranges. There is a faint sample, which is black. There is an intermediate sample, which is red. This is enclosing L star, all right, the knee of the Schechter function. And there's a bright sample, which is blue. So first of all, you notice that all three samples in both cases have this qualitative behavior that the clustering is falling as a function of separation. Qualitatively, they are very similar. Quantitatively, they look very different. Okay, so quantitatively, the M-peak sham has much stronger clustering at small separations than the M-vir sham. This is not very difficult to understand because the M-vir sham has done sham with M-vir, remember, and sham with M-vir, if you go back, sorry, I need this live. Okay, so sham with M-vir, if you remember, does very different things to satellites, right? So sorry, I interchanged. So now M-vir is on the left. Okay, so it gives, so M-vir, remember, has lower values for the same satellites than M-peak for the reasons that we discussed here. Okay, here is a satellite. Its M-vir value is 10 to the 10. Its M-peak value is 10 to the 12. Okay, so now imagine a catalog in which I have a bunch of satellites and they have some M-vir values and some M-peak values. Now, when I do my sham and I start traversing the scaling function that Nishi was talking about, the luminosities that would be attached to satellites when I am doing M-vir will turn out to be very, very low because their MVIR values are very, very low. Correspondingly, for the same satellites, if I attach a luminosity using MPeak, then that value of luminosity will be much larger. Sometimes by a larger, maybe by a factor 100 or 1,000 or something. Okay, so it can be substantially larger because the MPeak values are larger. And this sham is assuming a one-to-one relation. So how does that propagate into the clustering? What happens is now I am focusing on the same luminosity bin in both MPeak and MVIR, right? So what will happen is for the same luminosity bin, if I look at the MVIR sham, I will miss some satellites which I would have counted here because those satellites in the MVIR sham would have been given much lower luminosities. Okay, so this is more obvious in the brightest bin. All right, so look at the brightest bin. So here there are there is some number of satellites which had values of luminosity in this range. Those satellites would simply not exist in this luminosity range in the MVIR sham because they would have been dumped into lower values of luminosity. So why is that relevant for the clustering? It's because the clustering of these small separations is dominated by satellites. Okay, so if you go back here in this visualization, you can see that all the satellites come in clumps, right? And they have very, very small separations with respect to each other. Satellites in these clumps will have very, very small separations. In fact, what one can argue is that it will be very difficult to find central galaxies, two central galaxies with separations as small as the separations you can achieve with satellite galaxies. Okay, so if I go to this plot and I ask what is the smallest separation that I can find among all of these objects, it will not be as small as the kind of separation that I will find here. Okay, so satellites can reach very small separations. And finally, the 2-point correlation function is just a numbers game, right? So if I just go back, it's just DD by RR. How many pairs at a certain separation? So clearly, the satellites will contribute a lot to the number of pairs at these low separations. So if I manage to capture these satellites in this luminosity range, my number of separations will be higher compared to random. And if I miss those satellites, then my number of such separations will be lower. Number of pairs with such separation will be lower. So this explains the difference between these blue guys and these blue guys here. Okay. And now one can ask the question, which one does better compared to observations? All right. So I have now shown you, I have done a kind of cheating because what I did is instead of looking at projected correlation function measurements directly, what I did is to take from Zehavi's same paper values of what is called galaxy bias. Galaxy bias is nothing but the ratio of this correlation function divided by, so you look at this correlation function at large scales and you divide this by the correlation function, corresponding correlation function only of dark matter. Okay, so this is the correlation function of galaxies. You consider the corresponding correlation function of dark matter and you take a ratio between the galaxy and the dark matter correlation functions. And for the purpose of this session, that quantity at large separations is called a bias squared term. Okay, and in the question answers, you can ask me more about this bias. There's a whole theory of this, which I will not have time to go to. But because I wanted to show you some kind of comparison with observations, I just went to her paper where she has provided fitting functions for this bias as a function of luminosity. Okay, so I just calculated that fitting function for these different luminosity ranges, and I multiplied it by the 2-point correlation function of dark matter, linear 2-point correlation of dark matter, which is underlying the cosmology and the simulation that we were using. Okay, so, and I have produced I have just multiplied those values of bias squared from Zehavi with this 2-point correlation function of dark matter. And that's why you see that these dashed curves, they are just separated. They have the same shape as each other, and they're just separated in the amplitude. The amplitude is this bias squared term. Okay. And if the abundance matching is working correctly, then at large separations, the 2-point correlation function I get from my sham analysis should match with this dashed line, with the corresponding colored dashed line. All right. And what you see is that the match is quite good when you reach 20 MPC for MPeak sham. And it is not so good. This is logarithmic scale. So these are like 10-20% differences. Okay. And at lower separations, it can become larger. Whereas these dashed curves remain a reasonable approximation down to pretty small separations also, at least for a couple of these luminosity bins. So this is one way of seeing that this MPeak sham is doing better than the MWIR sham. Here, definitely for all the separations and all the luminosity bins, it is not matching the large scale clustering. Here it is matching the large scale clustering quite well. All right. So in this sense, the MPeak sham is doing better. And the physical reason why MPeak sham is doing better again is clear from the discussion of abundance of this tidal truncation effects that we were talking about, namely that the galaxy properties should be reasonably insulated insulated from the tidal effects that the host subhalo is experiencing, and therefore any kind of algorithm which ties together the galaxy properties like luminosity to the peak properties of the halo, like peak mass or peak Vmax, is expected to do slightly better. Okay, and this is what we are demonstrating here as well. Okay, so let me now just, I'm basically done with the results that we wanted to show. So let me just play a little bit. You can play along with me here. Okay, so let's just go back to this notebook, which I have shared with you. And now all I'm going to do is to introduce some more conditions. Okay, so now the numbers will also decrease. So we can maybe increase the total number by something. So I have made it 20,000. And now I'm going to say, for example, let me only select. Okay, so let's do the same thing we were doing before so that we don't spoil the plot. So let's say we define some xlim, ylim. Okay, this will just take a second. So xlim, let's say 0.03 to 40. Okay, and ylim from 1e minus 1, let's say, or let's say 1e minus 3e minus 1 to let's say 1e3. Okay, so this is our default plot. All right. Oh, sorry, I should make it 3 minus 2 so you see everything. Okay, so this is when I just chose, okay, let's do this again without anything. It'll take slightly longer to, okay, let's do it with the original thing only. Okay, so 10,000 objects. That gave me a cut of 12.55. Okay, and that gave me this correlation function. So now what I'm going to do is I'm going to keep the mass cut the same. Okay, so this part of the code remains the same. So this log MWIR min is the same value as before, but I'm going to go to a smaller set of objects by imposing a new condition. So let's look at the clustering of centrals and satellites separately. Okay, so sorry, so this is this. So let's look at the central clustering. So this is MOX. Remember, centrals means PID is equal to -1. All right, so let's run this. So this time now see from 10,000, it has gone down to 9,400. So there were about 6,000 satellites in the sample. And now notice what will happen here. So remember this cut here, because I know what's going to happen, I'm telling you to remember where this thing is cutting off. Okay, it's less than 0.1. Look at that. Yeah. So now the correlation function simply has no values in this log-log plot below this separation. So let's see why that happened. So let's do this in a slightly different way. So I'm going to define a variable xir, which will hold the values of the correlation function. And I can just show you the values of xir. So you see that the xir values at these low separations, right? So this is xir, and let me also plot rmid. So these are my values of the bins, 0.04, 0.05, 0.08, etc. And at these bins, xir is -1, -1, -1. What does that mean? If I go back to my definition of xi r is dd by rr minus 1. So 1 plus xi r is dd by rr. dd is the number of counts, okay, number of pairs. So if xi r is minus 1, then 1 plus xi r is 0. That means I have 0 counts there. So there are no objects, no pairs. Why should there be no pairs? Can someone think of a reason why there should be no pairs? Below some separation. If I only look at central galaxies, if I only look at parent halos. I'll wait for a couple of minutes for people to think.
Would they get merged if they will be below certain separation?
That's, yeah, you're along the correct lines. Can you say that a little better? So merged in what sense?
I mean, they will collapse, and I think they. I'm not sure.
So there is no dynamic. Can you mute because there's a feedback? So there is no dynamics here because you are given a set of points, right? You are given the set of centers. So there is no time that is evolving or anything. So this is just a description of the image that is given to you, the 3D image. So can you imagine? Okay, so can you visualize based on, let's say, this image, what might happen at very small separations if I look at only central objects? So imagine a set of central objects where I have restricted attention to a very narrow mass range. So all the masses are very identical to each other. And therefore all the sizes are also very identical to each other, very close to each other, similar to each other, I mean. Okay, so imagine all the objects have 100 kpc sizes. And now I do a clustering analysis like this, 2-point clustering. Is there a reason to expect that below a certain value of separation, I will simply not find any pairs of objects? It's very close to what you were thinking about. Okay, so I can give the answer. It's geometry, actually. It's very simple geometry. It's because these objects have sizes, right? These halos were identified with some sizes, and these parent halos by construction are halos which don't overlap with other parent halos. So that means if I have two parent halos of size, let's say 100 kpc each, then their centers can at best be 200 kpc from each other. They cannot be closer to each other than 200 kpc, right? Because if they were closer to each other, then the halo finder would not have identified them as separate objects in the first place. So there is an inherent exclusion that is built into the definition of central objects, of parent objects, which is defined by their sizes. So it is not surprising then that below a certain separation, which is defined by the typical sizes of objects that you expect, you will not find any pairs. Is that clear?
Yes, sir.
Okay. Okay, so good. So now let's do the opposite exercise where we only look at satellite objects. So I'm just changing that condition to not equal to -1 PID, and I'm going to rerun. So now remember, we'll only get about 5,000 something objects. Oh, sorry, 500 something objects, not 5,000. Okay, so very few number of objects. So in this case, because it will be very noisy, well, let me show you the result with this anyway. Okay, so now the clustering is so strong that it is not even fitting into the size that I showed here. Okay, so let's show this. Maybe go to 1E4. Okay, there we go. All right, so let me go back once more. Let me just put everything on the same scale. So this is with centrals. I'm going back to centrals. This is what it looked like. Very low clustering here, not going above 10. All right. And if I do it with satellites, sorry, it's very quick. And now with satellites, there's a very strong clustering, and it is also going to lower separations. Okay. And the other interesting thing that you're starting to see is there is this kind of feature now appearing, which was not there in the correlation functions that we were seeing before. So if you look at these correlation functions, Okay, it is sort of there, but not quite. Actually, here you might have argued that this is also more or less like a power law only. Okay, but now that we focus on satellite clustering, we will be able to see that this power law is actually a kind of a fake effect. It is a visual impression. But let's go to larger set of objects by factor 10. Okay, so you start seeing this kind of feature appearing. And this feature is very interesting because it is separating two regimes of clustering. It is separating the regime where satellites dominate inside individual halos. Okay, so this regime from this visualization here, it is the regime where you are only counting separations inside single objects like this, right? Because imagine if I am in a bin which is counting only objects which are separated by 0.1 MPC over H. Okay, this is 0.1 MPC over H. So look at this image. This is 60 MPC over H. So this is 10 MPC. So 1 MPC is one tenth of the difference between the ticks here. So 0.1 MPC you probably cannot even resolve on this image with your eye. Okay, so if you go really, really deep. So now I am in a bin, I'm counting only those pairs of objects which are separated by 0.1 MPC roughly. So none of them, almost none of them will be central galaxies, such objects. They can only be satellite galaxies. Okay, so you are in a regime which is completely dominated, and those satellite objects are obviously inside the same halo because the halo is not going to be smaller than 0.1 MPC, a halo which contains satellites. That kind of halo will be several hundred kpc in size. Okay, so well, 100 kpc is 0.1 MPC, but a big halo which will contain lots of satellites will be much larger than 100 MPC. It will be few hundred MPC. So 0.1 MPC will fit inside a single such halo. So this regime that you are seeing is called the one halo regime. Okay. And this break that you see here is basically because you are now going beyond the regime where the typical size of the object is equal to this separation. Okay, so the typical halos that contribute here, you can sort of read off from here that they will have a size which is roughly 2 mpch or so. Okay, in overall separation. So half of this will be the typical size of objects. And here what you see is the large scale clustering of these satellites. So if you go back here, you are seeing satellites from different halos. So this is called the two halo term. Okay, so at these large separations, which are like 20 MPC or something in size, you will find like here, 20 MPC means from here to here, right? So you will have to pick one object from here and one object from here, and so on. So this kind of thing allows you to play with not only the actual measurements, but also the underlying physical ideas which build up this kind of two-point correlation function. So I wanted to just leave you with these kind of things. We are coming close to the end of the session. So I think I will just stop here. There is nothing more that I wanted to say anyway. So we can have questions for not just me, but for maybe everybody else also. So 6 o'clock we have to end anyway. So we have about 20 minutes for general discussion.